So, after a brief review of signals, more specifically 2D signals and some of the interesting signals that will be routinely used, it's time now to review systems. Remember, we are going to take a signals and systems approach. So, in the imaging system, we have some input, right? We have an input which is our 3D spatial distribution. So, 3D object, but it is essentially human body, but you have some inherent signals of interest. So, we are a distribution of whatever property as seen by the principle of the imaging system. So, we will denote f of x y as the underlying input spatial distribution function, and your system is going to be represented by h, which is very typical. You would have seen this in typical 1D signals and systems, and then output image is going to be represented by g of x y. I mean, I will try to be as clear as possible as we go forward, but the general intention is to use f of x y for input and g of x y for output. Okay. So, what is a system? I mean, quickly to run through, what is a system? Oh, signal we covered. So, this is signal, this is another signal, right? So, what is a system? Well, as you can see here, anything that operates on an input at the broadest level, it is something that operates on the input to give you another signal. So, it operates on an input signal to give an output signal, right. So, in our case, it is going to be a spatial distribution at the input and a spatial distribution at the output. The objective of the system is to make sure the output is as close as possible to the input or the unknown underlying distribution. Okay. This is fine. So, essentially what this says is, you can use a system, right? You can use a system to capture the underlying, take the input and transform it into an output, which seems nice. I mean, it kind of connects everything, but it does not really tell you. We cannot really mathematically write it and do analysis of the system in this all encompassive manner, right. So, it is too general. So, what we need to do is, okay, system is something that operates on an input to generate an output is fine, but can we whittle down to some desirable conditions, right, or properties of such a system where we could write out the mathematical expression to convey this system operation, right, what the system does, what the system behaves. So, if you want to characterize, analyze the system, how do we write it down mathematically? Is there ways or simple assumptions that we can encounter or apply to make this happen? So, one of the first important property of a system is going to be linear, nothing different from what you would have known from 1D signals and systems. So, when you say linearity, what does it mean? Well, think about it. Immediately you may call about some theorems and say how to prove linearity, but what is the big picture? What does it try to convey? What does linearity imply physically, right? You have h of, right, this is your system. You have system. What is this? We really do not know. I just written some formulation, some representation. But what do we know here? Oh, we know this f of x y. What is this f of x y? That is my input. So, if you have to read this, what this physically means, it says this is some weight, let us call w as a weight. So, you have a function f of x comma y. So, if I give f of x y to this system h, if this h operates on f of x comma y, I get an output g of x y. What happens if I give to this system this signal, this input. What is this input? This means fk of x comma y. F of x comma y I know. What is this fk of x comma y? F1 of x comma y, f2 of x comma y. So these are different input functions. Each one has their own weightage. So weighted sum, right? This is a summation. So when you give an input, that is not one input, but it is a sum of weighted sum of several inputs. If you pass that through the system, the output, right? Output is going to be what? Output is going to be, oh, I have another summation here. I have the weights which is same as Wk. So it is sum of correspondingly weighted. This is the interesting deal. H of fk of x comma y. What is h of this guy? Oh, h of f of x comma y is g of x comma y, which was the output to that particular input. That means h of fk of x comma y means if the input was f1 of x comma y, the output would be h of f1 of x comma y would be g1 of x comma y. So essentially this represents the output to individual inputs f1 of x comma y, f2 of x comma y. So physically what does this mean? This means if I provide to the system, right, if I present to the system a weighted sum of different functions, right, the output of the system, right, the output of the system will be sum of correspondingly weighted output to corresponding inputs. Okay, so make it life simple. I mean, it's very similar, in fact, but for the variables used, very similar to your 1D, right, linearity. So you would have used t, but here you are using some x and y. So just to write it out, so if k is equal to 2, just have two signals, then a linear system satisfies the following. That is, when I present to the system a combination weighted sum of weighted combination of individual inputs W1 F1, W2 F2. So if I present F1, I know what is the output. The output is H of F1. If I present F2, I know what is the output. Output is H of F2. If I present a combination, weighted combination of this W1 F1 plus W2 F2, then the output is going to be corresponding outputs weighted by the same weights, corresponding weights, right, W1 and W2. Clear? So this is very important property, and why is this important? Then essentially we are getting to what happens if we can have a signal seen as a combination of signals. So we will treat everything with one input signal, and then we can perhaps use this linear system theory and say, oh, I can, if I can see any input given any signal, if I can break that signal as a weighted combination of multiple signals, right, then I know how to handle it. Okay, so it will become clear as we go forward. So the idea that I said is, okay, if you why is this powerful? Is there a way we could talk about some arbitrary signal? But before we move into arbitrary signal, the whole idea of reviewing signal before this class is there are some interesting signals. One of the first interesting signals that we reviewed was, it's not here, it is point impulse. Okay, so we would like to know, because we know everything about point impulse, we talked about its importance. What was the importance? What was the salient feature? Well, point impulse, the delta function. Remember, in 1D we call it delta function, here we called it as point impulse. Essentially what it did is, we noted that by itself its definition is fine, but it becomes interesting because it applies, right, it cooperates, it operates on a signal, and then you have some interesting behavior. recall one property we covered, right? Shifting property. So we'll come to that. So the idea is, okay, that is an interesting signal. Now what happens if you present that signal to the linear system, right? So what happens to the output if my input is a interesting signal? That interesting signal is nothing but a point impulse. As you know from your 1D, when I put delta function as input, what is the output? The output that you get is called as your system impulse response, right? Similar. Only thing is, we are going to call here, we call it as point spread function, because impulse, we talked about point impulse. So when it comes through the system, the point is spread. So the system, how does it respond to a point? It spreads the point. So it is the point spread function, okay, also called as the point spread function. So how do we write? Oh, so your h of x comma y, right? This is a arbitrary function, right? Epsilon minus epsilon and eta, we will talk about that. So what happens? This is your h system. So if I present my system, right? If I present my system with an input, what is this input? Oh, input is a point impulse delta, right? Delta of x comma y is how we define, but then we made it little more general by saying it can also be moved around, right? So we present with a arbitrary delta function which has an offset epsilon and eta. Then so this is the input into the system. The output is called your point spread function. So clearly this is good, right? So if I know about the system, if I can talk about the system, if I want to analyze the system, now all I need to do is analyze this h of the behavior of h of x comma y comma theta and eta. That will tell me about the system. But not so desirable thing is, it is a variable. There are 4 variables there, so it becomes common. It's a 4-dimensional signal. H becomes a 4-dimensional signal. 4-dimensional signal is good mathematically, it might be good, I mean, so it's good to work with it, but when you talk about practicality, it might be important for us to understand what the physical meaning of this is. Can we reduce it to a more tractable form, yet not lose the generality, not lose the underlying. See, mathematics always tries to capture the underlying physical meaning, right? So we shouldn't lose that part, but at the same time we have to make some conditions or look for certain assumptions, look for certain ways to reduce the mathematical intractability, okay. I mean, but it is doable, right, but it's not practical. So we will try to see if there is any simpler way that we can invoke certain conditions. First thing that comes to so before we do that, that's fine, let's just connect the two concepts. So now if you have an arbitrary input function f of x comma y, right? So if you have an arbitrary input function, this we know, right? The first slide that we started when system review, we said, oh, if you present it with f of x comma y, present what? The system. So it operates, h operates on the f of x comma y to give an output g of x comma y. So for an arbitrary input, I know my output, okay. So now the question is, how can I write an output if this is my input, right? If I am presented with the input that we see, right? So how do you, the interesting thing is this, oh, if you present the arbitrary signal f of x comma y, I get g of x comma y operating through the system. So that is good, right? But I cannot simplify that without knowing anything further about the h. But now I know something about the h. What is that h? Something that about h I know. Oh, that is the system impulse response. So I know if I present an impulse to the system, right? If I present an impulse to the system, I know my impulse response. So now can we think about presenting the system with impulse multiplied. So the arbitrary signal, right, f of x comma y, I can actually see that arbitrary function as a collection of impulse function at different locations. This is what we saw through shifting property, right. When you look at, go back and when you review the shifting property, you will recognize that any arbitrary signal f of x comma y can be seen as a collection of, right, you are using this delta function, go look, we can use that to pick points on the surface, right, from f of x comma y. So that is at, if you are picking it from epsilon comma eta, then the value of f is picked at that location, right. That is what your shifting property we covered, that is what we covered for your point impulse. So here essentially what we do is, I know something about this h, which is the system impulse response. How does it behave to the impulse? So now you see how cleverly an arbitrary signal f of x comma y can be seen as nothing more than a collection of, right, different locations. You have the impulse, you are picking off that value, and you have the double integral, your summation. So your g of x y, which is your output to a arbitrary input f of x y, can be connected through the behavior of system impulse response. Okay. So let us see. So this is good but not so good. The good news is now it seems like there is a mathematical form to connect the input and output. In fact, any arbitrary f of x y can be operated upon if I know my h of x comma y comma zeta comma I. If I know this, that is, in other words, if I know the system impulse, then I could generate or predict any output. Okay. So that is good, but what is not so good is, in order to evaluate this double integral, you have to know everything about this h, which may or may not be possible all the time. At least knowing h, all the 4 dimensions, may not be possible all the time. So what do we do? Of course, if you should have probably recognized this equivalent. So this is your superposition integral. Okay. Superposition integral connects your output to input and system function in the form of, right, integral. So this superposition theorem you would have studied, right, for linearity. So this is just an extension of it, but it gets little complicated because the dimensionality is increasing. Otherwise mathematically is a straightforward extension. So now what we will do, we will essentially proceed forward and try to see if we can address this issue. We have 4 dimensions for h. Can we reduce the dimension? Is there any way to make it little more mathematically tractable? So as you can see here, we will invoke this idea of shift invariance. So if you are wondering, oh, you know, I have done linear in 1 dimension, I have done it. So I know linearity is similar. What is the shift invariance? Probably I have not heard shift invariance as this, but you probably would recognize time invariance, because most of, like I said, most of the time in 1 dimension we talk with the time as your independent variable. So you would have heard something called linear time invariant system, right? That makes life lot easier for you in 1D. Similar thing here, we have an equivalent which is shift invariance. So that means what would it try to do? Oh, I have my impulse, instead of time invariance means you are moving along the time, the offsets in time, right? Here there should be shift in position, spatial shift. Whether your h is sensitive to where you shift or not is the idea here. So it turns out, if the system is shift invariant, then this is what happens. H of, so you have f of x comma y. If you have f of x comma y, the output is g of x comma y. if I present f of x minus x naught, y minus y naught, what does that mean? I have an input, but now I am moving the input, right? I am shifting it in the input space, and then I have a system. So what comes out of the system? The output. So the output shift by the same amount. Okay. So if this is my input, right, and I am moving, so if I shift my input, I present it through the system, my output moves exactly the same way, right, exactly the same way. That is what is your shift invariance. In other words, it does not matter how you arrived there. If it presented with that input f of x comma y, you get the output g of x comma y. If you shift the input, that is, you shift it in x naught and y naught, your output of your f of x comma y will also move by x naught and y naught. So why is this important? Now suddenly you see we had 4 dimensions, right? The h can be brought down to only 2 dimensions. Now I am not worried about shifts, I am not worried about the offsets, I am only worried about x and y, right, where it is and how it integrates with the signal. That is what is going to determine my output. Okay. So therefore LSI system, right, yields h of x minus theta, y of y minus eta as h of delta of this shift. So if I present a shifted input, right, delta functions, output is shifted version of the system function. This is very powerful, right. So using the shift invariance, if it is a LSI system, then this shifting of your delta function or point impulse just shifts your system impulse response. Okay. So now looking back to our superposition integral, right, we just saw that, and there was a h with 4 dimensions. So let us see what happens. So your g of x comma y, which is your output, is becoming f of theta comma eta times this guy. So now you notice suddenly it becomes little more tractable, right. So I can get my g of x comma y, similar concept, g of x comma y, I have f of theta comma eta in terms of my h, right. So system connections, input and output are related by the system function. Only thing is, it is now more compliant system. It is not only linear, it is also shift invariant. Okay. So this this looks complicated because of the variables are kind of new to you, but if I tell you just quick example, if you replace this x and y, right, or imagine this x and y is your t, right, and your theta and eta to be your tau. Now you of course you can even simplify it little further because of the denotions. You can call this y as g as y and input as x, right. Then you get, and of course you won't have 2 integrals, you will have d tau, right. X of t, h of t minus tau, d tau integral, you get y of t. This is your convolution. Only thing is its variables are different and you have one more dimension, so it looks new, but otherwise this is straightforward extension. Okay. So what is this? That means I expect that you know what that means. That is your convolution. So output is nothing but your input system response convolved with your input, that is your output. Clear? Exactly same or equivalent to your one dimension that you probably are very familiar. It is an extension. Okay. So nothing more to be taught there. Let us move on. Let us get some examples done, right. There will be homework or assignments where you will be able to work on some of this. again the level here is going to be just a review. So I expect that you go through the textbooks and signals and systems textbooks. You may have a lot of 1D, brush up your familiarity with 1D so that this becomes easier. So now the question is this linear shift invariant system? The deliberate reason I picked this is because most of you, when you look at this, you may probably pounce and say, oh, I know the answer. I mean, I eyeball, I know what it is. But the challenge in signals and systems, especially now that it is now 2D, is going to be when you try to solve something, then you will get a lot of confusion. Unless you are systematic in writing, right? If you had while you write, you are able to see the physical connection. Only then then it's a real material that you really have learnt it. If you eyeball and you feel, looking at it, I know, right? What will happen? Then probably if it gets to a difficult, see, I am deliberately taking some easy examples here, but in real world, it's going to be a lot more challenging. So if you have to bother with real signals, little higher signals that are a little more complicated, it's better you develop good habits. So write it out, right? So when you have like this, what do you do? First thing is what is linear system? Linear shift invariant system. So what is linear system? Linear system says if I am presented with arbitrary input, right? I mean, not arbitrary, sum of different individual inputs. So if I have F1, I get G1. If I get F2, I get G2. If I am presented with summation, weighted sum of, right? So let me. I think it will be good if you can write as we speak, right? So if I say, for example, just for clarity, I don't want to call it G of xy because we want to check whether G of xy is linear system or not. So if I say G dashed of x comma y is the output that you get when you present it with a combination, weighted combination of input signals, right? So let's say let's say you have a weighted combination. Let's say use the same variable k 1 to some capital K. So this you want to do with f of xk, f this thing, right? This is exactly from your previous slide. So I am calling this, right, the output to this is this guy. Rather, what should I say? Let's use the same variable. I mean, I don't have h explicitly here, so let's just, that's not equal to. So if this is presented to the system, right, this is the output. Okay, you see the carefulness here because I didn't have h here, so I am given the system, so h is hidden there. Okay, so this is the case. So let's see what is this a linear system or not? What happens if I do this? Oh, let's see what happens if I present this as the input. I am given the system here, right? So it is going to be, this is my input. So the output is going to be 2 times this guy, k wk fk of x comma y. Oh, of course, if this is the case, how do I mean, I could write it little more clearly as 2 times the input, just to recognize that this is f, this is x. The 2 is probably to do with the system. So let's just put a bracket, right? So this immediately you can recognize, okay, I can do this k wk, right? I can get the 2 inside, 2 fk of x comma y. So you can eyeball now. Of course, let's write the next step and say, if you eyeball now, what happens? Oh, this appears to be very recognizable, What is that? Oh, 2 times f of xy is gxy. So, 2 times fk of xy will be, or can be recognized as gk of x comma y. Clear? So, now what does this say? This is my g dashed of x comma y. So, when you read this out, what comes through? Oh, my new output, right, when presented with a weighted combination of inputs, right, my new output is nothing but correspondingly weighted sum of individual outputs to the individual inputs. Wow, isn't that what we defined as linear? So, that means it says g of x equal to 2 times f of x comma y is a linear system, because we just read it out, exact same physical interpretation of this relationship amounts to the definition for linearity. So, next is, is this okay, linear is fine. Is this shift invariant? What do you do for shift invariant? Oh, I need to shift the input. So, let us say if I present the input instead of f of x comma y, right, I present my g of x comma y, you get the output when I present instead of f comma y x minus x naught comma y minus y naught. If I present to the system, right, a shifted version of the input, what is the output? That is your g dash of x, right. So, then what happens? If I present this, then my, right, you look at this, look at here, if I present this as an input, my output is going to be 2 times, if I 2 times f of x minus x naught comma y minus y naught going to be g of x minus x naught comma y minus y naught. Oh, that is g dashed of x comma y is nothing but shifted version, right, both are same. So, essentially this is shift invariant as well. Clear? So, let us do one more, just we will not do it one more time. Again, now we can eyeball, but then we can eyeball with some steps written already. So, g of x comma y is equal to xy of f of x comma y. Is this a linear shift invariant system? So, looking at it, you can quickly see the similarity between this problem and the previous problem. Oh, if you recognize xy to be 2, right, pretty much you can follow the same steps. You can say, let us call g dashed of x comma y as the new output when presented with the system, when the system is presented with a collection of inputs, sum of collection of inputs, right, weighted sum of inputs. So, you can pretty much see that you can carry forward this. Only thing is, instead of this 2 here, you will have, when you pass it through the system, you will have output as x comma y, right. But you will recognize that if this is x comma y, it does not alter this equation, right. So, you will pretty much find g dashed of x comma y will be summation of wk gk of x comma y, which says that it is linear system. Is this a shift invariant? What do you do for shift invariance? Same thing, right. I have to shift the input. What happens to the output? Is that same as if I shift the output or the individual output? So, for example, if I do shift of input, right, f of x comma x minus x naught, f of y minus y naught. If that is my input, let us say I get g dashed of x comma y, right. This is my output. But if I look at here, what is my shifted output? G of x minus x naught comma y minus y naught. What is that? Oh, that is going to be x minus x naught into y minus y naught times f of x minus x naught y minus y naught. Clearly the x minus x naught and y minus y naught makes it unequal. So, if you shift the output, that is not same as, because you get x minus x naught into y minus y naught term, which was only x into y if you consider presenting delayed input. So, clearly it is not shift invariant. So, what the message is? Linearity, shift invariance, two concepts. If you have linearity, that does not mean it implies shift invariance or vice versa. Clear? So, that is something that is very powerful. So, we will end up using linear shift invariant system for our imaging system. I mean, I think the message should be very clear that it is not just because we can solve all this and get some easy mathematical traction. It turns out that this simplification does not really take away the ability to model, right, a general imaging system. At least most of the imaging systems that we are going to cover here, for the most common usage, I think linear systems theory is very much physically also very representative, right. We are not just doing things for mathematical traction, but it does not hold good in practice. I think this is powerful, yet powerful for the reason that it makes life simple, yet it does not really, it captures vast majority of the imaging systems. I mean, in our case, almost all of the imaging system that we are going to cover here introduce at least the most common imaging modes that are available. You will be able to get through this. Okay. So, let us just quickly run through few additional important aspects. So, we covered linear shift invariant system. So, now the question is, do we just have one system? What happens if you have more than one system? Right, usually this happens, right. You have subsystems. So, it depends on how you define input, what is output and what is the system. That is, so for example, in this case, if I am the input, right, I am say let us take the optical image, the camera that we have. So, I am the source, right, and then there is a camera system that is recording, then there is a audio system that is recording. All of this is compiled together, and that multimedia is streamed. So, that is one system, right. But then that multimedia is streamed using some internet, and then you are going to log in and probably download the video, and using your, say for example, mobile phone or a laptop or PC or whatever, that is going to read the data, right, and it is going to display it, and you are going to have some speaker or earphone or, right. So, you are going to listen and see. So, if you really look at it, input is this 3D distribution, output which you are looking, right, is a close or better be a close representation of the input. And then what constitutes the system here? Everything that went in between the input and the output, the true representation and the image that you see of me, right, that is your output. This is 3D is the input. Everything in between is actually one system as per what we have done, right. But then you see the problem. It is good. I mean, it's very general. We are able to capture that. I know what the system is. The system consists of the camera and the microphone that is there in the recording room, and then the PC that is used to process the data, and then the internet, and then your PC or your mobile phone, that subsystem. In fact, you then is the speaker output, or you are connecting it to some other home theater. Probably for this you won't connect to home theater, but I am just saying the idea is you have another. So, all these are, even though we said that it is one block system, you can actually see this as a series of subsystems. So, you can have multiple systems. It is about how you want to analyze, right. So, you are going to encounter, if I know how to characterize one system, that is why we talked about linear invariant, shift invariant system. Can we look at combinations of system, because there are going to be subsystems, right. So, what are the ways we can look at combinations of system? So, what we call as connections of linear shift invariant systems, right. How can you connect? So, let us take for example two systems, just so that we can eyeball and pat ourselves and say, oh, I understand it, right. But it is basically connection of multiple systems. But what are the ways you think you can connect two systems? Either you can connect through series, right, two systems in series, or you can connect two systems in parallel, right. So, that means when I say system, since this is linear shift invariant systems, each one, all I need to know is, if I know the H1, I say that is a system I know. If I know H2, that is my system, right. So, now what is the, if you connect them in series, as you can see here, it is equivalent to having only one system whose system function is nothing but that combines H1 and H2. How does it combine? This operator. What is that operator? Convolution. So, if I have, right, if I have an input F, the output of this LSI is going to be H1 convolved with F, and that output, right, H1 convolved with F goes into the input. What will be the output G? Oh, G is going to be H2 convolved with whatever went in. What went in? H1 convolved with F, that is the one that went in, right. So, you can then see, oh, that means my output and input are connected through this system, which is H1 convolved with H2, right. All these properties of commutative, associative, you know, right. I can do H1 convolution, the convolution properties, H1 convolved with H2 or H2 convolved with H1, right. All this you have to review, but otherwise you are getting one system equivalent. That equivalent, the system response is nothing but convolution of the two subsystems. This is in series. Similar logic you can extend if you have H1 and H2, right. So, what will be the output here? Oh, this will be H1 convolved with F, this will be H2 convolved with F. So, G is going to be nothing but sum of these two, right. So, if you have in parallel, that means you can reduce that to a single equivalent system whose impulse response or the system function is nothing but sum of the individual ones, clear. So, and these things will come in very handy, like I said physically when I talked about the example of recording and you seeing the video. Similar thing happens in the imaging system. You will have several modules of the imaging system, data acquisition, signal processing, display, right. All of this is a imaging system we say. So, there are several sub modules, and you will benefit from the ability to recognize that you can start to look at a complex system as a connection of subsystems, and therefore you know how to analyze. Okay. So, we will stop right here. We will start with the Fourier transform. Fourier transform is a very powerful concept. Whatever we did so far, we did in spatial domain, right. So, we started to look at signal, 2D signal as nothing but a spatial representation. Physical meaning was spatial representation of a pattern. Now, can we analyze, do the system analysis? Instead of convolution, can we have another aspect, another tool set that can be invoked, right, which brings us to Fourier transform. Okay. So, looking at this, you probably recognize it immediately. This is your Fourier transform and this is your inverse Fourier transform, right. So, let us stop here. I will actually start from Fourier transform in the next lecture.